What if I told you that the biggest roadblock to the quantum internet isn't actually the quantum physics at all?
Right, which is what everyone assumes.
Exactly. I mean, you picture this ultimate engineering dream, right? A world powered by scalable quantum computing, utterly unhackable quantum communications, ultra-precise metrology.
The Holy Grail, basically.
Yeah, the Holy Grail. But to make that dream a reality, to actually build the physical architecture for these networks, we need mass-produced, high-performance, integrated photon-pair sources.
We need chips that can just spit out entangled photons reliably, on demand.
And right now, the traditional manufacturing methods used to build those chips,
Okay.
they're creating a massive, massive bottleneck.
Oh, absolutely. We're kind of stuck in this frustrating paradigm. The very tools the industry relies on to build these quantum devices are, well, they're fundamentally limiting how well they can perform.
Because clean room techniques just weren't designed for this.
Exactly. They weren't designed for the hypersensitive optical tolerances that quantum states actually require.
And this is where you, our listener, come in. Because you're out there operating nanoscribe systems, constantly pushing the boundaries of two-photon polymerization, or 2PP.
Which is exactly why this topic is so relevant today.
Right. You already know the raw power of 3D microfabrication. But today, we are going to look at how your specific field is bypassing those traditional clean room nightmares to directly unlock the quantum internet.
It's a really elegant solution, honestly.
It really is. So we've got a fantastic set of source material for this deep dive. It's an August 2026 research article published in Optics Express.
By Mohammed A. Soadan and a team from Leibniz University, Hanover, right?
Yep, and Paderborn University too. So our mission today is to explore exactly how 2PP is being used to create high-performance photon pair sources on a periodically poled thin-film lithium niobate platform.
Which is a mouthful, but to appreciate the scale of this breakthrough, we really have to look at the substrate itself first.
The thin-film lithium niobate, or TFLN.
Right. TFLN is, it's essentially the silicon of the quantum photonics world.
It's that important.
It is. Because it has this exceptionally high second-order optical nonlinearity, specifically the Chi2 coefficient.
Which is what allows for the highly efficient three-wave mixing, right?
Exactly. And that is the fundamental physical mechanism we use to actually generate photon pairs. Plus, the TFLN platform supports just a huge range of optical functionalities.
Like modulation, frequency conversion.
Well, routing, yeah. You can do it all in one single chip. But the irony, the really frustrating irony, is that lithium niobate is incredibly difficult to physically shape.
Yeah, I was looking at the traditional fabrication methods the industry uses for this, like reactive ion etching or argon ion milling. The margin for error seems just impossibly small.
It's virtually non-existent.
You're basically bombarding a crystal with ions to carve out a microscopic optical waveguide. So if the sidewall angle is off by even a fraction of a degree,
or if the etch depth varies by, just a few nanometers.
right, your phase matching condition is just entirely ruined. Is that physical vulnerability why the industry is so desperate to bypass etching altogether?
That physical vulnerability is exactly the issue. Lithium niobate is chemically inert.
Meaning you can't just dissolve it nicely.
Exactly. You can't use a simple chemical wet etch to gently wash it away. You have to use physical dry etching, like argon milling.
Which is basically sandblasting the crystal at the atomic level, right?
That's a perfect way to put it. It's a highly non-selective process, and it leaves behind these really rough, damaged sidewalls.
Okay, let's unpack this for a second. It's like traditional etching is like trying to sculpt a microscopic canal out of marble.
Oh, that's a good analogy.
Right, one slip, one rough edge, and the water, or in this case, the light is just splashing everywhere and the whole slab is ruined.
And that splashing, that scattering is absolutely devastating. When you're dealing with quantum states and single photons, propagation loss means you are losing your entangled pairs.
You're just destroying the coherence of the whole system.
Completely. Plus, etching lithium niobate requires these agonizingly long development cycles.
Because of all the steps.
Yeah. You have lithography, etching, cleaning, metrology. And if you discover a defect in the waveguide geometry after all of that,
you can't just patch it up.
Nope. That entire chip and basically weeks of clean room time goes straight into the trash.
Wow. Which brings us to the actual brilliance of this Optics Express paper. The researchers looked at that etching problem and basically decided, not to play the game at all.
Right. They asked a completely different question.
They said, if carving into the material ruins it, how do we guide the light without ever touching the crystal?
And they bypass the problem entirely using a strip-loaded waveguide.
Built using your field's bread and butter 2PP.
Yeah, the structural setup of their device is just a masterclass in avoiding material damage.
Walk us through the physical layout.
Okay, so the base of this chip is a 600 nanometer thick layer of X-cut lithium niobate.
And that ultra-thin 600 nanometer dimension is critical, right?
Very critical. It forces the optical mode to remain tightly confined, which dramatically increases the light intensity and boosts the nonlinear conversion efficiency.
Okay, so that explains the physical layout. But the chemical composition of the substrate is highly specific too. It's doped with 5% magnesium oxide.
Yes, the MgO doping.
Because I know pure lithium niobate is notorious for optical damage at high laser intensities. So is this a stabilization measure?
It is a vital stabilization measure. When you pump high-intensity laser light through pure lithium niobate, you can actually trigger the photorefractive effect.
Meaning the light itself is messing with the crystal's properties.
Basically, yeah. The intense light excites electrons, they migrate through the crystal lattice, and they create these internal electric fields.
And those fields change the local refractive index.
Exactly, through the electro-optic effect,
Yeah.
which completely scrambles your phase-matching condition.
So the doping stops that.
Right. By doping it with 5% magnesium oxide, you drastically increase the crystal's conductivity. It allows those excited electrons to relax before they can build up any damaging electric fields.
Okay, that makes sense. And then all of that sits on a 2-micrometer thick silica buffer, which rests on a silicon substrate.
Right. The silica buffer essentially acts as an optical insulator.
Because silica has a much lower refractive index than lithium niobate.
Exactly. So it provides vertical confinement, it traps the light in the crystal layer, and physically prevents it from leaking down into the silicon substrate below.
Okay, so we've got this highly engineered, totally pristine stack of materials.
Untouched by any etching.
Right. And instead of cutting into that delicate lithium niobate layer to form the waveguide walls, the Hanover and Paderborn team just dropped some IP-dip2 photoresist onto the chip.
Loaded it right into a 2p2 system.
And printed a polymer strip directly on the flat surface. But wait, I have to ask on behalf of the listener here, if the polymer is printed on top, where is the light actually traveling?
It's a great question because the mechanics here can be super counterintuitive.
Yeah, I think a lot of people might assume the light is traveling entirely through the printed polymer itself, like a conventional optical fiber just laid on top of a table.
Right. But the physics of a strip-loaded design operate on a totally different principle. The polymer strip does not contain the core of the optical mode.
Okay, so how does it work?
Well, the IP-dip2 polymer has a specific refractive index of around 1.54 at these operating wavelengths, but the lithium niobate beneath it has a much higher refractive index.
It's around 2.2, right?
Exactly. So when you pump light into this system, the core of the light mode naturally wants to stay in that higher index lithium niobate.
The polymer still affects it.
It does. The evanescent field, which is like the outer edges of that optical mode, extends slightly upwards into the polymer strip.
Ah, okay. And because the polymer's index of 1.54 is higher than the air that surrounds the rest of the chip.
The presence of the polymer locally increases the effective refractive index of the lithium niobate directly beneath it.
Oh, wow. So you're creating a waveguide without actually carving one.
Exactly. That local increase creates a lateral refractive index contrast within the crystal itself. The light mode is squeezed laterally, guided right along the path of the polymer strip.
But the actual photons are propagating primarily inside the pristine, untouched lithium niobate layer beneath it.
You get all the tight lateral confinement of a carved waveguide, but the light is traveling through perfectly smooth, unetched material.
That is brilliant. You completely bypass the sidewall roughness and all that propagation loss that comes with the chainsaw approach to etching.
And because 2PP systems, like the ones our listeners use, routinely hit sub-100 nanometer resolutions, the team had exquisite control over the dimensions of that guiding strip.
Right. They printed the polymer strip to be exactly 1.5 micrometers wide and 2.6 micrometers thick.
And they didn't just guess those numbers. They ran extensive finite difference eigenmode simulations to arrive at those specific dimensions.
The FDE simulations.
Yeah, and the physical behavior those simulations uncovered really highlights the unique flexibility of this approach.
How so?
Well, the simulations revealed that the width of the printed strip, that 1.5 micrometer dimension, strongly dictates the lateral confinement.
Which makes sense. It dictates the modal dispersion and ultimately the phase matching condition of the device.
Exactly.
But wait, the thickness is 2.6 micrometers, which just seems surprisingly tall for a waveguide designed to operate in the single-mode regime. If the width is so critical to the optics, why push the height all the way up to 2.6?
That's the fascinating part. The simulations showed that the thickness of the polymer strip has a completely negligible effect on the effective refractive index of the guided modes.
Wait, really? None at all?
None at all, provided it's above a certain minimum threshold. Once the polymer is tall enough to fully encompass that evanescent field extending up from the crystal.
Which is usually just a micron or so.
Right. Once you hit that, adding more height doesn't interact with the optical mode at all. The light simply doesn't reach that high into the polymer.
So they locked in the 1.5 micrometer width to optimize the optical physics, ensuring single-mode operation. And then they just made it 2.6 micrometers tall for what? Pure fabrication convenience?
So, essentially, yes. It gives the printed structure mechanical stability. It prevents it from drooping or deforming during the development process.
And it does all that without interfering with the delicate quantum physics happening underneath.
Exactly. The ability to optimize the optical properties on the lateral axis and then independently optimize the mechanical printing stability on the vertical axis. I mean, that is a level of design freedom you simply do not get with standard etching.
Okay, so the polymer strip perfectly confines the light without scattering it.
Yeah.
But confinement is only half the battle here, right?
Right. To actually force this pristine crystal to spit out entangled photons, we have to manipulate its internal structure.
Using spontaneous parametric down conversion, SPDC.
Yes, which requires diving into the mechanics of periodic polling.
Okay, let's break down SPDC for a second. It's a three-wave mixing process where a higher energy pump photon is annihilated inside the nonlinear material, right?
Right, and it creates two lower energy photons. Traditionally, we call them the signal and the idler.
And energy conservation dictates that the sum of the energies of those two new photons has to perfectly equal the energy of the original pump photon.
Exactly. But here's the catch. Because of chromatic dispersion in the lithium niobate, different wavelengths of light travel at different phase velocities.
So the pump laser and the newly generated signal photons are literally traveling at different speeds through the crystal.
Yes. And without any intervention, they will very quickly drift out of phase with each other.
And once they're out of phase, the newly generated photons begin to destructively interfere with the photons that were generated just a fraction of a millimeter earlier, right?
Exactly. Your production rate basically crashes to zero.
So how do they fix that?
To prevent that destructive interference, you have to continuously reset the phase relationship, and they achieve this through periodic polling.
Which is a physical alteration of the crystal.
Yeah, they apply a high-voltage pulse through microscopic electrodes on the surface. It physically inverts the ferroelectric domains of the lithium niobate lattice along the z-axis.
So they're literally flipping the electric dipoles of the crystal back and forth in a periodic grating.
Every time the dipoles flip, the sign of the nonlinear coefficient flips with it.
Acting as a phase reset.
Exactly. It allows the amplitude of the generated photons to build up constructively over the entire length of the device.
And based on the effective refractive indices dictated by their 1.5 micrometer wide polymer strip, they calculated that this phase reset needs to happen exactly every 1.7 micrometers.
Which translates to a full polling period of 3.40 micrometers.
And they pulled a 3-millimeter section of the crystal with this highly precise grating. So in operation, they take a continuous wave laser diode, TM polarized, operating at 778.6 nanometers, and they pump it into the device.
And as that light travels through that 3-millimeter pulled section, the SPDC process occurs.
And because of that specific 3.40 micrometer grating, those pump photons split into two time-energy correlated photons, emerging symmetrically around a degenerate wavelength of 1557.2 nanometers.
Which lands perfectly in the telecom C-band, meaning these entangled photons can be seamlessly integrated into existing global fiber optic networks.
Which is huge for the quantum internet.
Huge. And notably, the team utilized Type 2 SPDC here. In Type 2 phase matching, the two generated photons emerge with orthogonal polarizations.
So one is transverse electric, or KE, And the other is transverse magnetic, or TM.
Right, which makes it mechanically simple to separate the signal and idler photons later using a polarizing beam splitter.
And that's a foundational requirement for creating certain types of polarization entangled bell states.
Exactly.
Okay, let's look at the raw performance metrics, because I want to know how efficiently did this strip-loaded architecture actually generate these pairs?
So operating at a very low input pump power of just 0.5 milliwatts, the device achieved an on-chip pair generation rate, or PGR, of 4.357 megahertz.
Okay.
And alongside that, they recorded a coincidence to accidental ratio, the CAR, of about 404.
Okay, I have to play devil's advocate and apply some analytical scrutiny to those numbers, because the authors explicitly mention other platforms in the literature hitting a 13 gigahertz PGR and a CAR of 150,000.
They do, yeah.
So on the surface, 4.3 megahertz and 404 seems, well, rather modest. Are these numbers actually good? Are we sacrificing massive amounts of efficiency just to avoid etching the crystal?
It's a really fair question, but the comparison is completely misleading unless we unpack the specific physics and the mathematical assumptions behind those figures.
Okay, break it down for us.
First, regarding the competing platforms hitting gigahertz generation rates, those devices almost exclusively use Type 0 SPDC.
Type 0 utilizes the D33 nonlinear tensor component, right?
Exactly, which is the absolute strongest nonlinear coefficient the material possesses. It's around 27 picometers per volt.
But Type 0 generates photons that have the exact same polarization as the pump.
Right, so you get high volume, but you lose the orthogonal polarization that makes Type 2 so incredibly useful for quantum communications.
I see, so it's an inherent trade-off.
Yes. Type 2 SPDC relies on a different tensor component, which is inherently much weaker, around 4.5 picometers per volt.
And since conversion efficiency scales with the square of the nonlinear coefficient, Type 0 will just always produce vastly higher raw photon counts.
Always. But the disparity isn't just about the tensor components. The way the industry calculates the pair generation rate is notoriously fragmented.
Right, because calculating PGR is tricky.
Very. The massive gigahertz numbers seen in other papers frequently rely on an alternative, much more forgiving calculation method. They calculate PGR based purely on the time average single photon counts hitting the detectors.
But if you rely on time average single counts, your detector is basically picking up everything, right?
Everything. Dark counts, stray scattered pump photons, uncorrelated background noise. It artificially inflates the generation metric massively.
So what happens if the researchers of this paper applied that looser calculation method to their own 2PP device?
Their on-chip PGR suddenly leaps from 4.357 megahertz up to a staggering 723.5 megahertz.
Wow. Okay, that puts it in perspective. So they chose the mathematically rigorous route instead.
They did. They calculated the joint detection probability. They looked only at photons that arrived at the superconducting nanowire single photon detectors at the exact same time. True coincidences.
And then they worked backward, explicitly factoring in the known transmission losses of their outcoupling setup.
Correcting the coincidence rates by the actual transmission loss yields that truer, albeit mathematically lower, 4.357 megahertz figure.
Which just shows that direct quantitative benchmarking across different papers requires extreme caution. You really have to look at the assumption.
You do. Furthermore, they deliberately kept the pump power low at 0.5 milliwatts to maximize signal clarity.
Because the CRR is inversely proportional to the pump power. Right?
Yes. If you crank up the laser to 10 milliwatts, sure, you generate far more entangled pairs, but you also drastically increase the probability of multi-photon emissions.
Generating 2 or 3 pairs simultaneously, which is multi-photon noise.
And that noise diminishes the CRR, which ruins the fidelity of your quantum network. So dialing it back to 0.5 milliwatts was a very intentional choice to optimize for a clean quantum state over just raw volume.
Okay, so the device performs admirably when analyzed within its correct physical context. But, and here's where it gets really interesting, the researchers didn't just stop at proving the device works.
No, they didn't.
They went on to demonstrate what makes this fabrication method genuinely revolutionary for the industry. They proved absolute reproducibility by utilizing what I'd call the ultimate trump card of two-photon polymerization.
So reusability.
Right, which kind of defies conventional cleanroom logic. I mean, if a standard TFLN chip has a microfracture in the etched waveguide,
Or if the lithography mask was slightly misaligned.
that chip is dead. Thousands of dollars, weeks of cleanroom time, completely unrecoverable.
But with this 2PP strip-loaded approach, the substrate is never permanently altered by the waveguide creation.
So if they get a bad print, or if dust gets trapped in the polymer, or if the lateral alignment with that polling grating is slightly off, what do?
They literally just drop the entire chip into an ultrasonic bath of acetone.
They basically turned a highly sensitive quantum photonic chip into an etch-a-sketch.
That is exactly what they did. The acetone chemically dissolves the IP-dip2 polymer entirely. It washes it away and leaves the lithium niobate completely untouched and unharmed.
You literally wash the waveguide off, clean the chip with distilled water and isopropanol, drop some fresh photoresist on it, and print the waveguide again.
It's a totally non-destructive iterative loop.
Yeah.
And the data from their reprinted chip provides a fascinating physical insight.
Right, because after they washed the chip and reprinted the exact same waveguide file, the performance didn't just match the original.
It improved dramatically.
The on-chip PGR jumped from 4.357 MHz to 14.569 MHz, and the TR skyrocketed from 404 to 3399.
It's a massive bump.
But wait, if they are printing the exact same digital file onto the exact same piece of crystal, the internal physics of the SPDC process haven't changed.
Nope. The polling period is the same. The nonlinear tensors are the same.
So where is this massive performance bump physically coming from?
The improvement was almost entirely due to a reduction in coupling losses at the physical interfaces of the chip.
Ah.
Yeah, when they measured the system after the reprint, they found that the outcoupling loss had dropped down to 18.2 decibels.
Which accounts for nearly the entire difference between the two generation rates.
Exactly. It translates to roughly a 3 decibel improvement in pair detection probability.
So during the first print run, there might have been a microscopic defect at the facet edge where the fiber meets the chip.
Or perhaps the polymer stitching along the waveguide had a tiny bit more scattering due to a minor mechanical vibration in the lab.
But instead of just living with suboptimal performance, they just erased it, rolled the dice again, and achieved a physically superior print at the interfaces.
This absolute reusability is a complete paradigm shift for industrialization. You can iteratively optimize the waveguide placement, the dimensions, and the facet quality on a single, expensive chip until it performs flawlessly.
It eliminates the catastrophic resource waste that plagues quantum hardware development.
It really does.
However, this perfectly highlights the major bottleneck limiting this device right now. Because even with the superior second print, the outcoupling loss was still a hefty 18.2 decibels.
Yeah.
And the incoupling loss was 5.27 decibels. Losing that many photons just trying to get the light on and off the chip, I mean, that's a severe handicap for any quantum network.
Oh, the authors are fully transparent about that. This coupling inefficiency is absolutely the primary hurdle.
So what's causing those losses?
They stem from two physical factors. First is Fresnel reflection, which occurs because of the stark refractive index mismatch between the lithium niobate waveguide facet and the air or glass of the collection fiber.
The light simply bounces off the interface.
Right. But the more significant factor is the mode overlap mismatch. The researchers are using a lensed optical fiber to collect the generated photons, and that fiber has a spot size of 5 micrometers.
But the waveguide mode emerging from that highly confined 1.5 micrometer wide polymer strip is entirely different in its shape and dimensions.
Exactly. When you try to force a tight elliptical optical mode into a large circular fiber core, the modes just don't physically overlap. A huge percentage of your precious entangled photons just scatter into the surrounding air and are lost forever.
Bridging that dimensional gap between microscopic on-chip waveguides and macroscopic fiber optics has got to be one of the hardest challenges in integrated photonics.
It is.
But wait a second. For someone in your field, our listener operating a 2PP system, the solution is sitting right in front of us.
I think I know where you're going with this.
If the main problem is the mode overlap mismatch at the edges, and they have a 2PP machine sitting right there, why can't they just program the nanoscribe to print 3D mode converters or microlenses directly onto the chip facets to perfectly shape the beam?
You hit the nail on the head. That is exactly what the authors propose as the mandatory next step.
That's amazing.
Right now, they are treating 2PP as basically a 2D planar lithography replacement, just printing a flat strip. But the fundamental advantage of two-photon polymerization is its 3D freeform capability.
Right, you could print the standard strip-loaded waveguide across the flat surface to handle the SPDC process. Then, in the exact same print job, without even moving the chip, you gracefully taper that polymer strip upwards and outwards at the edge of the chip,
physically expanding it into a perfect 3D parabolic mode converter.
Yes, And that 3D taper would adiabatically expand the highly confined optical mode, reshaping it as it travels toward the edge of the chip.
Until the mode-filled diameter perfectly matches the 5 micrometer spot size of the lensed fiber.
And if the lens shape doesn't perfectly counteract the Fresnel reflection or the mode mismatch on the first try,
You toss the chip in the acetone bath, tweak the CAD file, and try a slightly different curvature an hour later.
it creates a completely closed loop of rapid prototyping that addresses every single pain point of integrated quantum photonics. You preserve the pristine crystal substrate, you achieve precise phase matching, and you solve the packaging and coupling problems all with a single tool.
Exactly.
The researchers in Hanover and Paderborn took the dream of mass-produced quantum photonics and really removed the nightmare of traditional etching. By utilizing a 2pp printed IP-dip2 polymer strip on top of thin-film lithium niobate, they proved you can generate high-quality, telecom band correlated photon pairs without ever damaging the substrate.
They proved that a fabrication defect is no longer a death sentence for a multi-thousand-dollar chip.
They gave quantum engineering the ultimate physical undo button.
Which leaves us with a rather profound final thought to consider here.
Let's hear it.
The photonics industry currently views two-photon polymerization primarily as this brilliant tool for rapid prototyping and lab-scale experiments. But if this technology can print your waveguides, your perfectly tailored 3D mode converters, and your coupling lenses all in a single automated step,
And wash away any mistakes.
right, and literally wash away and correct any mistakes without substrate degradation. At what point does 2PP stop being just an alternative fabrication method? At what point does it become the undisputed industrial standard for mass-producing the physical architecture of the quantum internet?
A microscopic, iterative solution to a massive engineering dream. Thank you to our listener for joining this deep dive into the source material. You are the ones operating these systems out there, so keep pushing those boundaries. The quantum world is waiting to see what you print next.